Hey, this is Avi Gutman with another Ask Me Anything event brought to you by quantreasoning.com. I invite you to join me live next time. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial at quantreasoning.com. If we do word problems in Quant with this strategy of pause and make an inference, pause and make an inference, pause and make an inference, and if we're using number line reasoning, etc., if we're really practicing our reasoning for quantitative reasoning, a positive side effect of that, a byproduct, if you will, is that our verbal reasoning improves as well. Because in the end of the day, reasoning is reasoning. So quantitative reasoning and verbal reasoning both happen in the same part of the brain, and if you train yourself to better reason on the quantitative side, then you're automatically going to become better on the verbal side. On top of that, if you are doing your quant section first and then you're doing your verbal section, by using a lot more reasoning in quant versus math and algebra, you're going to have a lot more, let's call it brain power left over for the verbal section because you're just not working as hard. You're going to be less exhausted by the time the verbal section gets going. And I have seen with a lot of tutoring students over the years that by just working on quant with them, their verbal score really improved. We're about to look at the first question of the day, but I have a couple of disclaimers to make first. So the question we're going to look at now is not an official GMAT question. It's a question that I made up. It's in my book. But it could be an official GMAT question. So it's in my opinion, it's a good example of an official GMAT question. The second disclaimer is that the solution method that we're about to go through is not necessarily the best solution method for that question. So if I actually had that question on the test, I'd probably solve it in a different way, and that different way is also in the book. But what's good about the approach that we're going to look at here together is it's really going to improve our number line reasoning, and that will impact our ability on other questions, harder questions, etc. So that's the purpose of what we're about to do now. It's not about how do I get to the answer as quickly as possible. It's about what can I learn from this question and how can I use this question to improve my quantitative reasoning. So with those two disclaimers in place, let's look at the question. Okay, so the approach that we're going to use here involves translating the absolute values into English, into distances from 0. So the first step would be to say the following. The left-hand side, x plus 1, is located exactly the same distance from 0 as the right-hand side, which is 2 times x minus 1. Now, we could rephrase that again and say that x plus 1 is located twice as far from 0 as x minus 1 is because of this factor of 2 that we have in the previous sentence. So if something is equal to 2 times something else, then the first thing must be twice as big. In this case, twice as far. Then we can draw a number line and say, look, here's a number line with 0 in the center. I don't know which side of 0 x minus 1 is. It's either there or there. And x plus 1 is twice as far from 0 as x minus 1 is. So x plus 1 could be in one of those two positions. So this is me translating the equation that had absolute values onto a number line just to kind of visually see what we're dealing with. What are the possibilities? Now, what are the distances among the tick marks? Well, I know that the distance of x minus 1 from 0 is the absolute value of x minus 1. So we can just say that each of these gaps among the tick marks is equal to the absolute value of x minus 1. That's how far apart they are. Now, if you've been doing a lot of number line reasoning, then something in this image should be bothering you. There's something about this image that we're looking at that doesn't fit quite right, doesn't make sense. If you plot x minus 1 and x plus 1 on a number line, we know the relative order. X minus 1 is going to be exactly 2 units to the left of x plus 1. And that's always going to be true regardless of what x is, because the definition of minus 1 means 1 unit to the left on the number line. The definition of plus 1 means 1 unit to the right on the number line. So we can say that this is the true positioning of x minus 1 and x plus 1 on the number line, which means that one of the possibilities in the upper number line is nonsensical. X plus 1 can't be all the way on the left there to the left of x minus 1. So we can get rid of that as an option. We had here in the upper number line, we were basically saying, look, I don't know which side of 0 x minus 1 is. It could be on either side, so I have 2 tick marks there. But to be clear, x minus 1 can't be in both of those tick marks. It's one or the other. X minus 1 can't be in 2 places at the same time. So I don't know which of those tick marks is the true position of x minus 1, but I can say that it's one of them. Same goes for x plus 1. We inferred from the free info that x plus 1 is twice as far from 0 as x minus 1 is. So if x minus 1, well, regardless of which side of 0 x minus 1 is, x plus 1 will be twice as far from 0. Which side of 0? I don't know. So we plotted these 4 tick marks to show, like, 2 of them are the possible positions of x minus 1, and the other 2 are the possible positions of x plus 1. But then we recalled that we know the relative order of x minus 1 and x plus 1. That's always going to be the same. Always, x minus 1 will be 2 units to the left of x plus 1. But if that's true, how do you reconcile that with the 4 tick marks in the upper number line representing, claiming to represent the true positions of x minus 1 and x plus 1? One of them is nonsensical. And I hope you'll all agree with me that just going through this thinking is doing wonders for our number line reasoning, which is so useful on the test. So again, like I said in my disclaimer, I'm not necessarily doing this at the test center, because at the test center, my goal is to just get the right answer as quickly as possible. But at home, that's not my goal. At home, my goal is to improve my reasoning. So that's what we're working on here. Now, looking at what we have left here, I'm saying, I know exactly where x plus 1 is. That's the tick mark. That one on the right is the tick mark for x plus 1. But I have 2 possibilities for the actual position of x minus 1. So at this point, I could already say there are 2 possible values of x. Like going back to what the question was asking, what are the possible values of x? I can say now there are 2 of them. One if x minus 1 is to the left of 0, and one if x minus 1 is to the right of 0. We don't know which of those is the truth, so there are 2 possible values of x. So where do we go from here? I would suggest that we focus on just one of the options first. So I'm just going to start by focusing on this scenario where x minus 1 is to the right of 0. And then what I can bring in here is the observation that we made a couple of minutes ago, that we know how far away from each other x minus 1 and x plus 1 are. Remember, we had that observation? We can use that in the upper number line and say that this is 2. The gap between x minus 1 and x plus 1 is 2. So that's always going to be true. Which means that this is also 2. Between 0 and x minus 1. But the question is asking about x. So where on this number line would you find x? We have a tick mark for x minus 1. We have a tick mark for x plus 1. Where would you find x? That's right, x would be at the midpoint, the dead center between x minus 1 and x plus 1. Which means that x is equal to what? X must be equal to 3. I'll pause here for questions because it's going to be a bit more challenging with the second option. Let's see what happens when we focus on the other option. So I'm getting rid of the positive option of x minus 1, and now we just have x minus 1 on the left side. We can still use that observation that x minus 1 and x plus 1 have to be 2 apart. And if I were to use that observation here, knowing that x is at the midpoint between x minus 1 and x plus 1, and knowing that the total distance is 2, so let's put that up there. What would you say is each of the three distances that we have right below the 2? We have 3 equal distances. Their total is 2 units. That means that each of them is what? Each of these little distances is 2/3. And since one of those distances of 2/3 starts from 0, let's focus on that one. That means that this here, this tick mark is 2/3. And x is at the midpoint between 0 and 2/3. Which means that x is 1/3. Now we have our answer there at the top right. Now the solution that I would actually use at the test center is the first solution that I offer in the book for this question. So for those of you watching this on YouTube, that's an incentive for you to get the book to see the solution I would actually use. This alternate solution is great just for practicing our number line reasoning. It's a lot of work to do at the test center, so I wouldn't actually use this there. But the act of using it at home drives my number line reasoning to the next level. You need to think about what the operation -1 does on the number line. And you have to ask yourself, does it depend on my position on the number line? Like, does the actual impact of doing -1 depend on where I am on the number line? And the answer is -1 always means the same thing. Same goes for +1. Now, that's one of the biggest differences between additive reasoning and multiplicative reasoning. When you're multiplying, your position, your starting point on the number line is critically important. I mean, without knowing your starting position on the number line, you can't make any inferences whatsoever with multiplication. I mean, if you're at 0, there will be no impact of multiplying at all. And if you're positive, then multiplying by a positive factor would keep you on the positive side, but multiplying by a negative factor would flip you to the other side of 0. If you're more than 1 and you're multiplying by more than 1, then you'll move further to the right. And if you're a fraction and you're multiplying by a fraction, you'll move closer to 0. So all bets are off. We can't make any inferences whatsoever about multiplication if we don't know where we are in the number line. Addition and subtraction, though, the impact will be 100% predictable. Like, I know exactly what -1 will do regardless of where I am in the number line, and the same goes for +1. So that's the reasoning behind our inference that x -1 will be exactly 2 units to the left of x +1, regardless of where we are in the number line. Hey, I'm just going to interrupt my own video for a moment here. If you're finding value in this video, please let me know in the comments below, and give this video a thumbs up. It really motivates me to keep uploading a new video every day. Alright, back to the video. Let's start with a quick reminder of what greatest common divisor is and how to work with it. So if I'm talking, let's say, about 20 and 35, just as an example, and I want the greatest common divisor, what I would do is I would find the prime box of each of these numbers. So 20 is 2 squared, 5 to the power of 1. 35 is 5 to the 1, 7 to the 1. And the greatest common divisor, also known as greatest common factor, would be whatever those boxes have in common. So going back to a metaphor that I gave a few weeks ago about the clothing store that sells jackets of different sizes, and each prime number is a jacket size that's available, then for 20, the store has 2 jackets size 2 and 1 jacket size 5. And for 35, the store has in their inventory 1 jacket size 5 and 1 jacket size 7. So the greatest common factor would be, what can I say for sure I'll be able to purchase if I don't know which store I'll be going to? So I haven't yet decided which, like, imagine it's a chain, they have these different outlets. I don't know yet which one I'm going to. What can I guarantee that I can definitely pick up at the store, not knowing ahead of time which one I'll go to? And the answer here would be, well, I can get a jacket size 5. Regardless of which store I go to, I can get a jacket size 5. Anything else I can definitely get? without knowing which store I'll be ending up at? No. The only thing for sure I can get is one jacket size 5. So that would be the greatest common factor or greatest common divisor of 20 and 35. We would say that that's 5 to the power of 1. Okay, so that's just in general what is a greatest common divisor. Now, I think probably statement 1 is easier to evaluate in this question. What would you say to statement 1? If we know that m is a prime number, can we then tell what the greatest common divisor would be for m and n, without really knowing anything about n other than it's a positive integer? That's really all we know about n. N is some positive integer, so it's a store whose inventory we know nothing about. It could have no inventory at all. That's if n equals 1. Right? The prime box of 1 is just all the primes to the power of 0. 2 to the 0, 3 to the 0, 5 to the 0, 7 to the 0. That would be 1. So if n is 1, that means the store has no inventory whatsoever. And I know nothing about n, so it could have any inventory. And what do we know about m? It's a prime number. Can we now say what the greatest common divisor is for m and n? What do you think? Yeah, with statement 1 on its own, we can say that the greatest common divisor of m and n is either 1. That would be the case if n is not a multiple of m. Then the greatest common divisor would be 1. Or if n is a multiple of m, then the greatest common divisor would be m. So which is it, 1 or m? I don't know. Eliminate the answer choices that claim that statement 1 is sufficient on its own. Because the prime box of m only has m. It's the only thing it has. So you couldn't possibly have a greatest common divisor that's more than m, because m is the only thing that that store has. M is a prime number. But if n doesn't have m in its prime box, then the greatest common divisor is 1. Because there would be nothing in common between those prime boxes. Okay, statement 2 on its own. Statement 2 on its own is giving us a ratio. I know it doesn't look like a ratio when you glance at it, but one of the things we want to work on is translating an equation like this into a ratio. Are you able to tell me just from looking at the equation who's farther away from 0, n or m? Yeah, the two inferences we can make from statement 2 are, number 1, n and m are both on the same side of 0. Now in this case, they told us in the free info that they're positive integers, so we already knew they were on the same side of 0. But I'm saying more generally, if we didn't know anything, that equation from statement 2 implies that n and m are both on the same side of 0, and it also implies that n is farther away from 0 than m is. Specifically, I mean, we could even go as far as to say n is 3.5 times as far from 0 as m is. Why? Because in order to bring n and m to the same place on the number line, all you have to do is double n, while at the same time multiplying m by 7. So that means that, you know, since m needs a bigger factor in order to match it up with n only requires a factor of 2, m requires a factor of 7. From that I can infer, drawing a number line, that n is 3.5 times as far from 0 as m is. Now if you wanted to do it algebraically, you could divide both sides by m, like this, and then divide both sides by 2, like this, and then rewrite that equation horizontally. So it would be n to m is 7 to 2. So now I have it as a ratio. It was given as an equation, but now it's looking a lot more like a ratio. And we have an integer constraint here. So what does that mean? Since our ratio is fully reduced, 7 to 2 is a fully reduced ratio. There's no common factor between 7 and 2. And since we know that n and m are positive integers, we can infer now that the actual value of n is a multiple of 7, and the actual value of m is the matching multiple of 2. So we could say that the actual value of n is 7k, and the actual value of m is 2k, where k is some positive integer, and it's the scale factor of this ratio. So that's what we can say from statement 2. So I'll ask you all, now that we know the ratio of n to m is 7 to 2, can we tell what the greatest common divisor is? Wouldn't it be true, though, to say that given what we have here, where we have the actual value of n as 7k and the actual value of m as 2k, wouldn't we then be able to say that the greatest common divisor is k? They're both terrible statements. With statement 1, there's an infinite number of possibilities because we don't know the value of m. And with statement 2, there's an infinite number of possibilities because we don't know the value of k. All we know is the ratio of n to m, but we don't know what the scale factor is for that ratio, and whatever that scale factor is, that would be the greatest common divisor. What if we combine these statements? Yeah, the only multiple of 2 that is a prime number is 2. By the way, that's true for any prime. The only multiple of 11 that's a prime number is 11. The only multiple of 7 that's a prime number is 7. So you can also use the ratio that we have here at the bottom. We already said m is equal to 2k, where k is some positive integer. But if you're telling me m is a prime number, well, now I know that m is exactly 2, which would then mean that n is exactly 7. And you know what's cool about this is that even if you don't know how to find the greatest common divisor of 2 and 7, you know that it's possible to find the greatest common divisor of 2 and 7. I mean, if I know what the values are, then somebody smarter than me who's PhD in mathematics would be able to find the greatest common divisor of 2 numbers as long as he knows what those numbers are. So the minute you can infer by combining the statements the actual values of m and n, which again would be 2 and 7 respectively, you're done. The correct answer is C. One could find the greatest common divisor of 2 and 7 if one wanted to. Of course, we know the greatest common divisor would be 1 because there is no common divisor other than 1 for 2 and 7. There's no common factors for those two numbers. And by the way, the greatest common divisor of any two prime numbers is 1, by definition. As long as they're different. If they're the same number, then that would be their greatest common divisor. The greatest common divisor of 11 and 11 is 11. But the greatest common divisor of two different prime numbers is always going to be 1, well, because they're prime. They're only divisible by themselves and 1. So I think this question is a bit unusual because it's asking us for the difference in the amounts of times that some task takes, depending on which machine is working. And we've seen in previous sessions that we can make a lot of inferences about the ratio of the amounts of times that a task takes. And the way to do that is to take the reciprocal of the ratio of the rates. So if one machine is 3 times as fast as the other machine, then it would take 1/3 as long to do the job. So we've seen that. If it's 5/3 as fast, it would take 3/5 as long to do the job. But here, they're not asking for the ratio of the times, they're asking for the actual difference, I guess, in hours, right? How many more hours does it take? So we're talking about a difference in hours between the two machines. And what I'm thinking is that if I can infer the ratio of the rates and the ratio of the times, those are inferentially equivalent, if I can infer that, I still wouldn't be able to figure out the difference in number of hours. In order to find the difference in number of hours, I would actually need to know how long something takes someone. Maybe if I knew how long it takes them together, or if I knew how long it takes one of them on its own, then I could use ratios to infer the difference in the amount of times that it takes. But without an anchor point in the world of actual numbers, actual hours, it would be impossible for me to answer this question. So with that in mind, I go to the statements, and what I'm surprised to see with these statements is that there is no anchor. We're not getting an actual quantity of time. So in my opinion, this question was designed by the test makers to be solved without any pen and paper. And this question was designed to test whether conceptually we understand that it would be impossible to answer this question without any actual quantity of hours. That's why I think they designed this question. And so the correct answer here is E. But I do think that it's also worth noting that I believe these two statements should be inferentially equivalent. We should be able to infer statement 2 from statement 1 and vice versa, which in and of itself eliminates answer choices A, B, and C, as I explained in the second section of the book. Without even reading the question, we can just look at the statements and say, hey, if I know 1, I can infer 2, and if I know 2, I can infer 1, and that eliminates answer choices A, B, C. And then when you read the question, you say, okay, I can also eliminate D because I don't have any actual quantity of hours. Knowing ratios is never sufficient if you want to find an actual value, unless you were also given an actual value. So this is the scale factor. We talk so much about the scale factor. The scale factor is the bridge that connects the world of ratios to the world of actual numbers. And, if you remember back in the day when maps were in physical paper, and there was a scale usually in the bottom right corner that showed you, that 1 inch translates into 30 miles or whatever. Without that scale, you could infer ratios. You could see that the distance from New York to LA is 7 times the distance of New York to Toronto. I don't know if that's true or not. I'm just making that up. You could tell that from a map without the scale, but you could never tell anything about actual distances between any two cities without being given the scale. So that's kind of what's going on in my mind when I look at this question and say, yeah, this is E. This is E, and I don't need pen and paper. And I'm not worried that, if I do some work with these ratios, maybe a number of hours will magically reveal itself. That doesn't happen. Percents are multiplicative in nature, so that would be a ratio. Whereas what they're asking here is additive. They're asking how many more, not how many times.
Okay.
Right? How many times would be a ratio? What percent more would be a ratio? How many more? That's additive. So let's actually build the ratios for these two statements and see how they're inferentially equivalent. We're told in statement 1 that together they take 2/3 as long as x on its own. So from that I can say that the rates, x to together is 2 to 3. That's the rates. And from that I can infer that the rate of y is 1, because the rates are additive. The rate of y plus the rate of x equals the rate together. So 1, 2, and 3. That's from statement 1. What does statement 2 tell us? The machine y takes twice as long as machine x. Well, I already knew that from here. Machine y would take twice as long because it's half as fast. And vice versa, if I'm given statement 2, so y takes twice as long, so this is ratio of times, convert to ratio of rates is 1 to 2, and then together you add them and you get 3, and that part of the ratio is what statement 1 gave us. So we can see how statement 1 implies statement 2 and vice versa, and that's why I was saying earlier we can eliminate A, B, and C. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.